Imagine a city rising from red dust. No human hands, no construction crews, no architects standing on scaffolding. Just machines, intelligent, tireless, and precise, assembling humanity's greatest achievement across 140 million miles of empty space. What you are about to witness is not science fiction. This is the plan already in motion. Scientists have confirmed it. Engineers are building it. And the robots are almost ready. Within the next 2 decades, autonomous machines will break Martian ground, lay foundations, pressurize habitats, and construct an entire city before a single human ever steps foot on the surface. The question is not if, the question is how. What kind of machine could survive minus 80-degree temperatures, dust storms that last months, and an atmosphere with almost zero oxygen and still build a city? The answer will change everything you believe about robotics, artificial intelligence, and the future of human civilization. Stay with us, because this story starts right here on Earth. Welcome to the frontier of space construction robotics. Across research labs, NASA facilities, private aerospace campuses, and advanced manufacturing floors, a new generation of machines is being designed, tested, and perfected not for Earth, but for Mars. These robots are unlike anything ever built before. Companies like NASA's Jet Propulsion Laboratory, Icon Technology, AI Space Factory, and private ventures backed by aerospace giants are pouring billions of dollars into one single mission, building machines capable of autonomous planetary construction. The factories producing these robots operate 24 hours a day, 7 days a week. This is not a moonshot dream anymore. Construction robots have already been tested in Earth analog environments, deserts of the American Southwest, the frozen tundra of Antarctica, and simulated Mars habitats sealed inside climate-controlled warehouses. The technology exists. The mission is already being engineered. Step inside one of these advanced robotics manufacturing facilities, and the first thing that hits you is the scale. Enormous production floors stretch for hundreds of meters. Overhead crane systems carry massive machine components. The air smells of fresh metal, polymer compounds, and hydraulic fluid. This is where Mars begins. Raw materials arrive in massive shipments. Aerospace-grade aluminum alloys, carbon fiber composites, titanium structural components, and advanced polymer materials. Every single gram matters. Because every robot eventually built here must survive a 7-month voyage through deep space before performing its first task on Martian soil. The production line begins with precision cutting systems. Computer-controlled laser cutters and water jet machines slice metal components to tolerances measured in microns, fractions thinner than a human hair. One miscalculation at this stage could mean mechanical failure millions of miles from the nearest repair shop. Perfection is not optional here. Enormous industrial robotic arms, some stretching nearly 12 meters, move in choreographed sequences, picking up freshly cut components and feeding them into welding stations. The sparks are blinding. The heat is immense, but the robots don't flinch. They weld continuously, creating structural joints strong enough to endure Martian atmospheric pressure cycles. Every weld is immediately inspected by machine vision systems. High-resolution cameras and laser scanners map each joint in 3 dimensions, comparing the result against digital blueprints in real time. If a weld fails even a fraction of the specification, the system flags it, stops the line, and triggers an automatic re-weld sequence. Nothing passes unless it is perfect. But what happens next changes everything, because building a robot for Mars is not just about making it strong. It must think. Deep inside the facility, entire wings are dedicated to AI integration, programming the neural networks that will allow these machines to make independent decisions 140 million miles from any human command center. The AI systems being installed into Mars construction robots are fundamentally different from anything used in traditional manufacturing. These are not simple program sequences. These are adaptive learning systems, capable of analyzing terrain, identifying structural problems, rerouting construction plans, and solving unexpected challenges entirely on their own, without asking for permission. In a temperature-controlled clean room, engineers carefully install sensor arrays onto robot chassis units, LiDAR systems, thermal cameras, ground-penetrating radar modules, atmospheric pressure sensors. Each robot becomes a walking data collection station, constantly feeding environmental information into its onboard AI processor as it works. The locomotion systems are engineering masterpieces. Mars robots cannot use standard wheel platforms on highly uneven terrain. Instead, engineers are developing multi-legged walking systems, articulated track platforms, and hybrid mobility units capable of climbing 45-degree slopes, crossing boulder fields, and maintaining stability during Martian dust storms with wind speeds exceeding 100 kilometers per hour. Assembly of the locomotion systems alone takes weeks of precision work. Hydraulic actuator systems are installed joint by joint. Each movement axis is calibrated. Each motor controller is programmed, then stress tested again. Engineers push prototype robots through thousands of simulated movement cycles before a single unit is approved for advanced testing. On a massive test floor designed to simulate Martian gravity, using counterweight suspension systems, prototype robots walk for the first time. Their movements are deliberate and powerful. Watching a Mars instruction robot take its first steps across artificial red gravel is strangely emotional. These machines will one day walk where no living thing has ever walked before. But movement is only one challenge. The robots must also carry and manipulate construction materials in Martian conditions. Testing rigs simulate the thin Martian atmosphere, just 1% the density of Earth's air, to ensure hydraulic systems, pneumatic tools, and mechanical grippers function correctly under drastically reduced atmospheric pressure. Most Earth-designed tools fail immediately. The solution comes from completely reimagined tool systems. Electrically actuated construction tools replace pneumatic ones. Sealed bearing systems replace open-air mechanical joints. Thermal regulation systems are built into every component housing to prevent metal contraction failures in minus 80-degree surface temperatures. Every single part of these robots is engineered from scratch for Mars. Deep inside the facility's AI development division, software engineers are writing the decision-making algorithms that will guide these robots during construction process. Unlike traditional construction software with fixed instructions, these systems use reinforcement learning. The AI learns from simulated mistakes, developing construction strategies that no human engineer explicitly programmed. One of the most critical systems being developed is autonomous 3D printing construction. Using a technology called contour crafting, robots will 3D print entire building structures using Martian regolith. The loose surface soil of Mars, mixed with polymer binders carried from Earth. The walls they print will be 1 meter thick, radiation shielded, and pressure sealed. Watching a contour crafting robot demonstrate its system on Earth is genuinely breathtaking. A large format robotic arm moves in precise overlapping layers, extruding material in concentric circles. Wall by wall, hour by hour, a sealed habitat dome rises from the ground. What once required hundreds of human construction workers, one robot accomplishes completely alone. But the Martian city will not be built by one robot. It will require an entire coordinated robotic workforce. Engineers are developing swarm coordination systems, where dozens or hundreds of construction robots work simultaneously on different tasks, communicate with each other through a shared AI network, and automatically dividing labor without human instruction. The swarm coordination system is tested here on Earth in a massive outdoor testing ground. Dozens of prototype robots are released simultaneously. Within minutes, the AI network assigns roles. Some robots level terrain, others begin foundation work, others deliver material, others begin wall construction. The coordination is silent, seamless, and extraordinarily efficient. It looks like choreography. Material logistics on Mars represent one of the greatest engineering challenges of the entire project. How do you supply construction material to robots working kilometers apart across unfamiliar terrain? The answer is autonomous supply chain robots, smaller unmanned vehicles that continuously transport materials from storage depots to active construction sites around the clock. These supply robots use GPS-independent navigation because Mars has no GPS satellite network. Instead, they rely on onboard terrain mapping AI, visual landmark recognition, and inter-robot communication to navigate. Every supply robot constantly updates a shared terrain database, making the entire robotic fleet smarter and more efficient with every passing hour of operation. Inside the quality control laboratory, completed robot units undergo final validation testing. Every sensor system is calibrated. Every AI module is stress tested with simulated Mars scenarios, including sensor blackouts, sudden terrain collapses, equipment failures, and dust storm interference. The robot must demonstrate autonomous problem-solving capability before receiving final mission approval. One test scenario sends a robot into a simulated terrain collapse. The ground beneath its work site partially gives way. The robot pauses. Its AI analyzes the structural failure. Within 11 seconds, it has rerouted its construction plan, moved itself to safe ground, and resumed work using an alternative approach. No human gave it those instructions. It figured it out alone. The electrical power systems for Mars construction robots represent another extraordinary engineering achievement. Solar panels alone cannot reliably power heavy construction equipment through Martian dust storms that can block sunlight for months. Engineers are developing compact radioisotope power systems, nuclear battery units, that provide continuous power regardless of weather or time of day. With power, mobility, intelligence, construction tools, and coordination systems all validated, the final stage of production begins. Full robot units are assembled on dedicated final integration lines. Each robot receives its complete sensor suite, AI core, power system, and construction tooling, then sealed. Then tested one final time as a complete autonomous unit, ready for deep space. The artificial intelligence systems powering these Mars robots represent the most advanced autonomous decision-making technology ever deployed in a construction application. Central AI controllers manage thousands of variables simultaneously: terrain data, material inventory, structural engineering parameters, atmospheric conditions, and robot health monitoring, all processed in real time. Machine vision systems aboard these robots are capable of identifying structural defects invisible to the human eye. High-resolution multispectral cameras scan every surface they encounter, analyzing material density, detecting subsurface voids, identifying potential failure points before construction begins. These robots see the world in ways humans physically cannot. The Industrial Internet of Things networks connecting the Mars robotic fleet operate through a mesh communication system. Every robot is both a data receiver and a data relay node, meaning even if one communication link fails, data continues flowing through alternative paths across the network. The system is designed to be completely failure-resistant. Predictive maintenance algorithms monitor every mechanical component on every robot in real time. Vibration sensors detect early bearing wear before failure occurs. Temperature sensors identify motor stress before burnout. The AI automatically schedules maintenance windows, routes repair robots to service units in the field, and minimizes construction downtime across the entire fleet. Energy optimization systems manage power consumption across the entire robotic workforce with extraordinary precision. The AI calculates optimal task scheduling to ensure maximum work output during peak solar generation periods, while shifting lower energy tasks to periods of reduced power availability. The system continuously rebalances energy distribution across hundreds of simultaneous operations. A central mission control data system, operating from Earth, receives constant telemetry from the Mars robotic fleet. Engineers monitor construction progress in real time, review structural integrity data, and transmit updated mission parameters when needed. But because of the 20-minute signal delay between Earth and Mars, every critical decision must be made autonomously by the robots themselves. The 20-minute communication delay is one of the most humbling challenges of this entire mission. By the time an engineer on Earth sees a problem on Mars and sends a response, 40 minutes have passed. The robot must have already solved the problem independently. This means the AI aboard these robots must be capable of handling any situation without waiting for human guidance. Real-time production analytics systems track construction milestones with extraordinary granularity. How many cubic meters of material have been printed today? What is the current structural integrity rating of Habitat Module 7? How much power remains in the depot storage systems? Every metric is tracked, analyzed, and optimized continuously by the central AI management system. The efficiency metrics achieved during Earth-based simulation trials are staggering. A coordinated swarm of 50 Mars construction robots can theoretically complete a 6-module pressurized habitat cluster capable of housing 12 people within 18 months of continuous operation. That is faster than most Earth construction projects of equivalent complexity using human workers and conventional equipment. The precision engineering standards applied throughout this program exceed anything previously attempted in construction robotics. Structural tolerances are measured to sub-millimeter accuracy. Pressure seal integrity is validated to certification standards far exceeding anything required for Earth construction. Every single joint, every single printed layer, every single mechanical connection is engineered to last decades on Mars. And here is where the conversation gets deeply uncomfortable. Because as these Mars robots demonstrate their extraordinary capability, the same technology is already transforming construction on Earth. Automated construction systems are beginning to replace human labor on building sites worldwide. The Mars mission is accelerating an automation revolution nobody is fully prepared for. Economists estimate that advanced construction robotics could displace up to 40% of manual construction jobs globally within the next 20 years. That represents tens of millions of workers whose livelihoods depend on skills that machines are rapidly acquiring. The Mars mission is inspiring, but the economic disruption it accelerates demands serious conversation. At the same time, the technology being developed for Mars construction is creating entirely new industries on Earth. Companies specializing in robot maintenance, AI system design, remote construction management, and autonomous fleet coordination are growing rapidly. New jobs are emerging, but they require fundamentally different skills than the jobs being displaced. The global manufacturing transformation driven by this technology extends far beyond construction. The same autonomous robotic systems, AI coordination networks, and machine vision technologies are being adopted in aerospace manufacturing, defense production, and advanced infrastructure development. The question is no longer whether automation will reshape industry, but how fast and how completely. Ethically, the Mars construction program raises profound questions about the role of human beings in a future increasingly shaped by autonomous machines. If robots can build cities on another planet without human presence, what does that say about the future of human labor, human purpose, and the definition of meaningful work in a world where machines can do almost everything? The next generation of factories may look nothing like what exists today. Fully autonomous production facilities, where AI manages every process from raw material intake to finished product delivery without permanent human staff, are already being prototyped. The Mars mission is not just building a city on another planet. It is writing the blueprint for the future of manufacturing on this one. Stand back for a moment and consider the full magnitude of what is happening. Human beings, for the first time in history, are engineering machines specifically designed to build civilization beyond Earth, not as a distant dream. As an active, funded engineering program with real robots on real test fields making real progress right now, this is a turning point. The relationship between humanity and machines has always been one of partnership. We built machines to extend our reach, to do what our bodies could not. And now, we are building machines to extend our reach across the solar system itself. These robots are not replacing humanity. They are carrying humanity forward into a future we could not reach alone. When the first Mars construction robot activates its systems in the thin red atmosphere of another world, begins leveling terrain, begins printing walls, begins building the first structure ever constructed on another planet, that moment will define a new era of human history, and it will have been made possible by engineers, scientists, and the remarkable machines they dare to create. The city on Mars will be built, not by human hands, but by human minds, translated into machines of extraordinary intelligence and capability. If this documentary opened your eyes to what is coming, hit that subscribe button right now, because we are just getting started. Drop a comment below. Would you live in a city built by robots on Mars? Share this with someone who needs to see it. The future is already being built, and our next video will take you even deeper inside the machines making it happen.